Greetings to the respected faculty. My name is Lasya Mandapati and I am from CSE AI&ML B section. My roll number is 24951A6686 and today I'll be presenting on Lagrange's linear equation, an important concept from our differential equations and vector calculus course. Let's start by understanding what Lagrange's linear equation actually is. It's a first order partial differential equation, meaning it involves only the first derivatives of a function typically denoted by z with respect to two variables, usually x and y. It takes the form of capital P capital Q. Capital P small p plus capital Q small q is equal to capital R, as you can see in the second point here, where capital P, capital Q and capital R are functions of x, y, and z, and small p small q represent the partial derivatives with of z with respect to x and y, respectively. This setup allows us to model systems that change in more than one direction at a time. For example, the way heat spreads across a metal or how a fluid flows over a curved surface. Solving such an equation provides insight into the behavior of the system in a highly structured and predictable way, making it easier to design solutions in a real-world engineering problems. The equation we're studying today is named after Joseph Louis Lagrange, one of the greatest mathematicians of the 18th century. Lagrange's work wasn't limited to just differential equations. He also made significant contributions to mechanics, calculus of variations, and number theory. The beauty of Lagrange's methods was his ability to simplify complex systems into manageable mathematical forms. The idea behind his linear equation was to create a standardized method for solving a class of partial differential equations that previously lacked a general application. Today, Lagrange's ideas still influence fields like vector calculus, optimization, and even areas of modern physics like quantum mechanics. It's fascinating to think that modern methods developed centuries ago continue to form the foundation for cutting edge research. Now, let's dive in to the structure of Lagrange's linear equation. As mentioned before, its standard form is Pp plus Qq is equal to R. Here, capital P, capital Q, and capital R are functions. And the equation is linear because small p and small q appear to be the first degree and are not multiplied together or raised to any power. Importantly, there are no second order or mixed derivatives involved. This simplicity is what makes it solvable using characteristic methods. By setting up what's called auxiliary equations based on the ratios of differentials, we can trace paths called characteristic curves along which a solution can be constructed. Think of it like navigating through a mountainous landscape. If you follow the correct paths, you can map the entire terrain systematically. Let us now discuss how this equation is derived. Suppose z is a function of x and y. By the chain rule, the total differential dz can be written as p dx plus q dy, where p and q are partial derivatives with respect to x and y. Now imagine that the relationship between x and y and z is governed by another constraint expressed in terms of the functions capital P, capital Q, and capital R. Setting up an equality involving capital P dx plus capital Q dy is equal to capital R dz, and rearranging it appropriately leads to the standard form. A key assumption here is that the function z is smooth and differentiable, meaning there are no sharp edges or discontinuities. This derivation is more than just algebra. It reflects the underlying structure of many physical systems where smooth changes happen over time. To build better intuition, let's look at the geometrical meaning of Lagrange's linear equation. Each solution represents a surface in the three-dimensional space defined by z is equal to z of x comma y. The characteristic curves we find by solving the auxiliary equations are paths that lie on the surfaces. Each point on the characteristic curve is tangent to the surface, meaning that the direction of the curve matches the slope of the surface at that point. You can think of it like the flow lines of a river over uneven terrain. They follow the natural curves of the ground. By finding these curves, we effectively trace out the surface, solving the partial differential equation indirectly by solving a simpler ordinary differential equation for each path. Now, now Let's get into the actual method for solving the equations. First, we set up the auxiliary equations, which are written by as dx by capital P is equal to dy by capital Q is equal to dz by capital R. These ratios represent how changes in x, y, and z are related along the characteristic curves. We then solve these two at a time to find two independent relationships along x, y, and z. These solutions are often in implicit form. Finally, the general solution of the PDE or partial differential equation is given by an arbitrary function phi of the two integrals we found. Symbolically, it is written as phi of u comma v is equal to 0. In practical problems, you may sometimes be given boundary conditions or additional constraints that help determine the specific form of the solution. Let's walk through an example together. So let's solve the equation y minus z into p plus z minus x of q is equal to x minus y. First, we identify capital B, capital Q, and capital R. Here, p is equal to y minus z, capital Q is equal to z minus x, and capital R is equal to x minus y. We set up our auxiliary equations. Dx by capital P is equal to dy by capital Q is equal to dz by capital R. Solving these two ratios at a time gives us two independent relationships. Typically, we solve the first two ratios first and pair the second and third, or the first and third. After integrating, we get two independent functions u and v, which involve x, y, and z. Then the general solution is phi of u comma v is equal to 0, where phi is an arbitrary function determined by boundary conditions or specific problem requirements. Let's solve another example. Z minus z plus y of p plus z minus x of q is equal to x plus y. Here, as you can see, capital P is equal to z plus y, capital Q is equal to z minus r, and capital R is equal to x plus y. Again, we write the auxiliary equations. Dx by capital P is equal to dy by capital Q is equal to dz by capital R. Solving the ratios gives two independent relations between x, y, and z. Suppose we solve the first two ratios and find one relation. Then we solve another pair to find the second relation. Once we have two independent integrals, we write the general solution as phi of u comma v is equal to 0. This structured approach ensures that we systematically solve for the entire surface that satisfies the original partial differential equation. You might wonder, where do we use Lagrange's linear equation in real life? The answer is almost everywhere. It appears in fluid dynamics, where analyzing how liquids or gases flow over surfaces. It's used in conduction problems to model temperature distributions over time. Engineers use it to analyze stress and deformation in materials. In aerospace, it helps calculate trajectories where forces vary with position. In image processing, similar partial differential equations model how images can be smoothed or enhanced. Even weather prediction models involve solving differential equations of similar structure. Understanding Lagrange's method gives you a foundational tool to tackle a wide range of scientific and engineering tools. When solving Lagrange's linear equations, some common mistakes include misidentifying capital P, capital Q, and capital R, or making errors in setting up and solving the auxiliary equations. Always remember that the two integrals must be independent, and the final general solution must be checked thoroughly and carefully. Mainly, remember to thoroughly check each step of the problem to ensure that there are no loss in constants during integration, errors while solving ratios, or forgetting the general solution forms. To summarize, we've covered quite a bit today. We introduced Lagrange's linear equation, explored its historical development through the work of Joseph Louis Lagrange, and explained its standard form. We then derived it using basic calculus tools like chain rule and understood its geometrical meaning by relating it to surfaces and characteristic curves. We also learned the systematic method of solving it using auxiliary equations. We walked through two auxiliary examples, saw where Lagrange's equation is applied in real life, and finally discussed some common mistakes to watch out for. I hope this presentation gave you a clear roadmap for understanding and solving problems involving Lagrange's linear equation. Thank you for listening to my presentation. I hope you have a nice day.